All right, so this is going to be the second video, I suppose, in our series of notes that we've taken on accelerated motion. Like I promised before, I'm going to try and do some of these videos for each one of these units, or at least a video for each one of these units. But this is the set of notes that you would have missed if you were not in class on Friday, September 3rd. Maybe you just want to, check out the video because you wanted to go back over some of the content. Maybe you're still struggling with assignment 4, whatever the situation might be. This is what we had done together in class that day. So it's got like one example, probably. No, it does. Sorry, that's what I was going for when I designed this series of problems. It's got one example of each style of problem that we could do. The only difference between this video and the last video that we worked on together, I suppose, is the direction that it's moving. And the fact that things that move vertically up and down, where gravity is the cause of that motion. We'll talk about gravitational forces later, but when gravity and acceleration due to gravity is the reason the object is speeding up or slowing down, it doesn't change the equations that we use. It doesn't change the approach that we have. It just means we always know what our rate of acceleration is. And that rate of acceleration is 9.8 meters per second squared in the downward direction. Typically in this class, because I'm not trying to beat anyone up with too much mathematics, especially for the multiple choice part. If it's good enough for the AP curriculum, then it's good enough for Mr. Willis. If we're using gravity in a particular problem of any kind, the easiest thing to do is just start with recognizing that we can round that. I like using -10 for gravity just because we can have conversations about exactly how an object's velocity will change or its displacement will change per second without having to do complicated mathematics, without having to pull out a calculator and continually multiplying or dividing by 9.8 every single time. After a while, that just gets annoying and difficult to keep up with. If we're using 10, all we have to do is move a decimal point, and it makes the conversation significantly quicker, and we can talk about what it is that's happening and why it might be happening as opposed to getting hung up on the numbers. That's really what this class is about. So just like the last worksheet that we did together, we are going to start by making a list of things that we know from the problem. Mr. Willis drops his phone off the stadium, the bleachers outside. If I count 3 full seconds as this object is falling, that's my time. How tall, and this is still just our position, but it's our position on the y-axis. So we're going to set it up as delta y instead of delta x like we did in the last set of notes, but it doesn't change the equations we're using. How tall is that set of stadium bleachers? The thing that is making the object fall is gravity. So we always know gravity. We can assume gravity is -10. If we're doing a lab, we'll use 9.8. But in all of our stuff that we're doing, it's going to be in class for homework and notes and quizzes and exams. It's going to be -10. So we need to find that position, that new position, the distance that this thing fell, while it was falling for 3 seconds at that rate. The other things that we could potentially know, again, I like to just use delta y. Really, it's y that we're looking for, with y0 being set at 0 meters, which essentially just means, as I'm standing up there on this set of bleachers and I drop my phone, we're setting this position at 0, and it will fall in the downward direction, and this position at the bottom is what we're looking for. So because we set its initial place at 0, and we're just looking for how far from 0 it goes, oftentimes I will just write that as delta y instead of using both y and y0, or if we're talking about horizontal displacement, x and x0. But the other pieces of information that were not provided are your 2 velocities. We know, based on this word right here, that your initial velocity is going to be 0. I did not throw this up into the air. I did not throw it down at the ground. We'll talk about horizontal, right? You can throw things at angles from the horizontal all the time, right? That's how, every sport ever works. You throw it at some angle from the ground. But I dropped it. so its initial velocity is 0. No information was provided about your final velocity. So if you look at your list of equations from the cover page, we have to use all of the information that we've got here to find our change in position while recognizing we cannot pick an equation that contains final velocity. The only equation on the cover page that does not contain final velocity is y equals y0 plus v0t plus 1/2 at squared. That's the only equation we can use. So this is why I had that conversation about y versus y0 at the very beginning. Obviously, we know what each of those are, but the cool part about it is when we go to plug in what we have, we'll recognize some of these things will disappear. So I'm going to include that y0 as a term just so that we don't get in the habit of thinking that it will always be gone. It will always just not be, it will never be something we have to worry about. It might. It just so happens in this case, we set that value to be 0, so it's not something we need to worry about. The other thing we can do is recognize that our initial velocity does the same thing. Right? Our initial velocity, because we dropped it, we didn't throw it up into the air, we did not throw it down at the ground, we didn't throw it at some angle in between, our initial velocity is 0. So this whole term right here goes to 0. Doesn't matter how long the object is falling for. If it's not falling, it has that whole term doesn't exist. Right? If it had 0 initial speed, then it's not there. And so really all that lasts, all that makes it through to the end, is the 1/2 at squared. In reality, some physics teachers will say if you're doing a drop problem, you can use delta y equals 1/2 at squared, and they call it the drop equation. I don't like giving this to you as its own unique equation because inevitably people will think that they can just jump right to this equation right here, and you can't. If the initial velocity had been anything other than 0, you must include it as a term before 1/2 at squared. So please be very careful. I write the whole thing, and if they're zeros, then you can plug them in as 0 and you can move on with your life, and it does get easy. If they're not 0, you have to account for them. So our change in position, the distance that this thing is going to fall, is 1/2 of -10 meters per second squared multiplied by 3 seconds squared. One quick reminder, 3 is the only number that gets squared. So 3 squared is 9, multiplied by 10 is 90, -90, divided by 2, your change in position is -45. But wait, there is more. We're not done. You're going to lose 1/2 point if you don't provide the correct units. Now, how do the units of meters show up in this big mess? Remember, when you square a value, square anything in parentheses, you're squaring the units too, and so you've got 2 units of seconds, and then in the denominator for your acceleration, you had 2 units for seconds, and that's why meters is the only unit that remains at the end of that problem. That's the justification or rationale for how we wind up getting those units of meters there. The other important thing to notice is that, yes, this should be negative because you begin at 0 and you end up 45 meters below where you were. Negatives in physics just imply direction. In my bank account, they make me sad. However, in this case, they just imply direction. That's all they mean for physics. So that was example number 5. Good old-fashioned drop problem. I discourage you from writing the equation that I have in red there on your equation card. It's the long one. If everything starts at 0, it might not always start at 0. Please be very careful. The follow-up to this is, what would its velocity be when it hits the ground? So, knowing all of the previous information that I've got an acceleration, I've got a time, I now know my change in position. They're asking for the final velocity. Technically, there's not an equation that we cannot use. So for this particular one, I'm going to start rewriting all of that stuff that I had up there. It was falling for 3 seconds. Acceleration due to gravity is -10 meters per second squared. My initial velocity was 0 meters per second. I'm looking for my final velocity. I don't know what it is. It's probably going to be in meters per second. You could go ahead and get yourself half a point of credit on the exam just by telling me what units this thing is going to have. And we know that its initial position we set at 0 meters and its final position will be negative 45 meters. All of that came from example number 5, right, from the previous problem. So when I say I don't care what equation you choose to use, I mean that sincerely. There will be a couple of equations that you shouldn't use, particularly this one. A lot of folks in class were asking, why can't we use this equation in order to solve for this? And the answer isn't that it has delta x in the numerator versus delta y. Remember, these are interchangeable with x and y. It doesn't matter. It just depends on whether or not you're moving up and down or left or right. This equation came from the linear relationship of position and time being a straight line. It was your slope is equal to your change in your y-axis over your change in your x-axis. And that's literally where we got v equals change in position over time. Those two are the same equation. We just changed the symbols. So this represents a linear relationship where your acceleration is 0. It only works if your acceleration is 0. If your acceleration is anything other than 0, then you have to use one of the other equations. The equations you can use are a equals delta v over t, or you can use v squared equals v0 squared plus 2a delta x, or delta y, just depends on whether or not you're talking about left and right or up or down motion. And then x equals x sub 0 plus v sub 0 t plus 1/2 at squared. So those are the options that you have. I think there's an average velocity on there too, but that's silly. You just add up the two speeds and divide by 2 because it's an average. Anyways, when picking an equation to solve for your final velocity, we can't use this equation because the acceleration is not 0. It's not traveling at the same speed. Every second it is falling, it is moving 10 meters per second in the downward direction faster than it was before. So we can't use that first equation. We have to pick one of these bottom 3. Truth be told, it doesn't matter which of the bottom 3 you choose. I'm going to pick this one because it's the only one that doesn't contain something being squared. It's the easiest of the equations, but all of them will work if you plug the correct numbers in the correct place. Personally, that's one of my favorite parts about physics. It doesn't matter what equation it is you choose. And that's the other reason why I always ask you guys to show your work. It's one of the most annoying parts of physics. I understand that. However, if you mess up a step somewhere, I need to be able to know what it was you were trying to do so that I can get you all the partial credit that you deserve. Otherwise, I have no idea what you were trying, no idea where you went wrong, and your wrong answer is just wrong, and you get none of the points, and that would really be upsetting for all of us. I think that's the easiest way to go about solving it. Technically, you could use either of the other two equations if you really wanted to. They just involve values being squared. So if you want to try them, go for it. If you want to practice your mathematics, give it a shot. But it's not going to be, at this point on the exam, you would just pick whichever one is easiest. So that was example number 6. Let's move on to example number 7, talking about maybe not dropping things, because that's really about all there is with dropping things. Let's talk about throwing things up into the air. To do so, I'm actually going to get rid of this and start a fresh page, because this one's going to have a lot of drawings. There's a couple of things that we have to talk about. First thing I want to talk about when we do this particular practice problem, this particular style of problem, is just what happens when you throw something up into the air. When you throw something up into the air, in this particular case, I'm giving it an initial velocity of 22 meters per second. I'm going to give it a positive 22 meters per second because, again, positives and negatives just imply direction. What acceleration due to gravity legitimately means is that every second of time that passes, your speed increases, your velocity increases by 10 meters per second every second. it increases by 10 meters per second every second in the downward direction. So if you drop something, then it just adds that negative velocity and it keeps getting larger and larger and larger and more and more and more negative. If you throw something up into the air, then it's a positive velocity and a negative acceleration, just like assignment number 3 with like a car hitting the brakes. A negative acceleration means you slow down. As you throw this ball up into the air, 1 second later, let me erase that and clean it up a little bit. 1 second later, your velocity will decrease by 10 meters per second. So 1 second later, this ball is not traveling 22 meters per second anymore. It has lost 10 meters per second in that 1 second, and now it's at 12 meters per second. And it will continue on because it still has positive velocity, and when it reaches whatever position it would have at 2 seconds, its velocity is now positive 2 meters per second. The reason I'm bringing this up is because eventually something's going to happen. In between second number 2 and second number 3, in that time interval of 1 second, between 2 and 3 seconds of being airborne, this ball that the juggler threw up into the air will run out of speed. And at the top of every object's flight path, at the top of every object's trajectory, its velocity will be 0 meters per second. At some point, it will run out of speed, right? The only way to not have this be the case would be to reach escape velocity for whatever planet or celestial object that you're on, which changes. We'll talk about escape velocities when we get to gravity, but it's really fast. I don't quote me on it. I have to look it up on Google. But I want to say that escape velocity for Earth was somewhere around 7 miles, 8 miles per second. None of the things that we will be throwing will traverse 7 miles in a second. So I think we're okay. When we say velocity for all objects thrown up into the air, at the top is going to be 0. Now, a test question, the velocity at the top is 0. The acceleration at the top, I could ask you, what is that? Everyone's gut reaction is to say 0. It's not. It's negative 10. Gravity does not care what you're doing. Gravity does not care if you're moving up, if you're moving down, if you're moving left, if you're moving right. Gravity is constantly trying to bring things down back to the Earth at 10 meters per second squared. That's a gross oversimplification of gravity, and we'll talk about that more when we get to gravity at the end of first semester. But as far as we're concerned right now, gravity is always negative 10. So what happens with all things that you throw up into the air? They turn around and they come back down to Earth. And that's what winds up happening. So why did I bring this up? I brought this up because if you look back at example number 7, we're only given one number. You're given the fact that the initial velocity for this ball is a positive 22 meters per second. They ask you how high up in the air does it go? Okay, well, you can find that change in displacement, describe your initial displacement as 0 meters. If on an exam you want to ask, can I just assume y0 or x sub 0 is 0? Can I start this at 0? I'll give you a thumbs up or a thumbs down. That's an easy thing. I'm not trying to trick you on that. So I've got 3 variables so far. The other pieces of information that I know is the thing that's going to cause this to come to a stop, turn around, and fall back to the Earth, and that's gravity. Acceleration due to gravity is negative 10 meters per second squared. I do not know anything about its time being in the air. That's not provided. That's not given to me. Oops, time is just seconds. I was moving on in my head while still talking about something else, right? So I don't know how long it's going to be in the air for, how many seconds it'll be in the air. It's not asked about. It's number 8, but we'll get there. So the other bit of information is the velocity, and this is why I brought up this. They asked how high up in the air did this object get? So if they're asking me about its change in position, we can label this as y0 at 0 meters, and it goes up. At some point, it will run out of speed. When it does run out of speed, it will turn around and come back to the Earth. But that's the position they're asking about. What is its velocity at that position? 0 meters per second. That's why I brought that part up, right? At some point it runs out of speed, and we know its velocity at the top. All of these objects, we know their velocities at the top. So they ask us about your change in position. We don't know anything about time, so you're going to go back to your list of equations, and you're going to pick the one equation that does not contain the letter t. There's only one of them, and that is v squared is equal to v sub 0 squared, your initial velocity, plus 2a, and in this case, it's going to be delta y. You're changing your y position because it's moving vertically. On the cover page, I wrote it as delta x because most of the stuff we started with was horizontal motion. Plug in what you know. My final velocity at the top is 0. My initial velocity going up was 22 meters per second. And we have gravity. We're looking for the change in position. Order of operations. We have to move the 22 squared first. So 22 squared gives me 484. I'm going to move it to the left. That makes it negative 484. All right, because it was being added, so we have to subtract it from both sides. That's going to give me negative 20 delta y. Check out both of those values now being negative. That works because this went up in the air, and the upwards arrow, the upward direction, is always positive. So we should get, what is that, divided by 20? 24.2. meters. That's how high in the air we went. All right. So the next question, because they asked us how high up in the air it went. The very next question continues off of this. If the ball returns to their hands at the exact same position, basically they threw it up in the air, their hand didn't really move a whole lot, and then they caught it as the ball returned. If the ball returns to the same position, how long would it be airborne? So we're asking, how long is it going to take this ball to travel all the way back down to y equals 0? I'm going to go back to my list of things that I know. I know that it was thrown up into the air with an initial velocity of 22 meters per second. I know the velocity at the top is going to be 0. I don't know what I'm going to be able to do with that, but I know it's going to be 0. I know acceleration is negative 10 meters per second squared. I know that my change in position was a positive 24.2 meters. I could label my initial position as 0, sure. I don't know t. That's what they're finally asking me for. So there are two ways we could do this. And I'm going to show you the easy way. Well, they're both relatively easy. I'm going to show you the two ways to do it. The first way is actually what I typically will teach regular physics to do. And that is because we know our velocity at the top. Why not use your velocity at the top? Oops, there we go. Why not use your velocity at the top? So I'm going to break it in half and deal with half of the object's trajectory. I think it's a J. Is it a G? Doesn't matter. Whatever. I'm going to erase it so I don't look silly. We're going to break this problem in half. We're going to do the first half of the problem. We have got this object being thrown up into the air, and at some point it will reach a velocity of 0. So easiest equation that we could possibly use. Our velocity at the top is going to be 0 meters per second. Our initial velocity was 22 meters per second. Acceleration due to gravity is negative 10. And time is what we're solving for. So move 22 over. Negative 22 is equal to negative 10t. Divide both sides by 10. This is why I like using 10 instead of 9.8. And the amount of time it took to reach the top was 2.2 seconds. That's going to be important. We didn't solve this yet. That's just how long it took to reach the top. It then has to turn around and come back down. So if it's got to turn around and come back down, this is the long way to do it. I don't encourage this. This is going to be a little cheat that I'm going to show you once we answer it. We know that it's going to fall 24.2 meters. So if I go back to that delta y equation, recognizing that my velocity at the top is going to be 0, right? The velocity at the top. Let's actually just write all of this in red so that it's less confusing, so you can see exactly what motion I'm talking about. If I'm just interested in its motion coming back down, then my velocity at the top being 0 is my initial velocity. And so I can take y, change in y, is equal to v0t plus 1/2 at squared, was that equation that I was using. And because my velocity at the top was 0, that term disappears. So if I fall down 24.2 meters, gravity is the thing that made me fall down, and I'm looking for t, then this becomes pretty straightforward. I get 24.2 divided by 5, because that's half of gravity. I get 4.84 is equal to t squared. Take the square root, and I'm going to get 2.2 seconds. Technically, you get positive and negative 2.2. I understand. But negative time just doesn't make sense. The book's got a whole section in there about whether or not values make sense physically. And you need to ask yourself, does negative time make sense? No, we can't go back in time. Here's the thing I wanted you to see. Those are the exact same number. And that's a really, really crucial piece of information that we can use moving forward, right? The idea behind this is that if you throw it up into the air, the only thing that is causing its speed to change at all ever is gravity. Gravity does not care if you're moving up, moving down, moving east, moving west, moving wherever. It doesn't matter. Gravity is always working at the same rate. So if you travel 24 meters vertically over the course of the amount of time it takes gravity to strip you of all of your speed, and then you turn around and travel 24 meters vertically the other way, gravity is going to give you back the exact same amount of velocity that you had. It's going to take the exact same amount of time to travel that distance. So your time to the top and your time back down are always going to be the exact same if you return to the same position you started. So we could have just taken that 2.2 and multiplied it by 2, called it a day. We could have been done. Or the other really cool thing you could do is use the exact same equation, recognizing that your velocity going up at positive 22 meters per second for 2.2 seconds is going to be the exact same velocity that you have coming back down, because gravity gave you back that same amount of velocity that it took away, right? Going from 22 to 0 takes the same amount of time as it does to go from 0 back to 22, because gravity is the only thing doing this for you. So the other way you could have written this first equation could have been negative 22 is equal to 22 plus negative 10t. And the reason this works is because your final velocity coming back down is negative 22. Your initial velocity going up was a positive 22. You move the 22 over, you get negative 44, and that is equal to negative 10t. Divide both sides by negative 10, and you get 4.4 seconds for the time it took gravity to take you from positive 22 meters per second to go up into the air, turn around, come back, and return at negative 22 meters per second. I think blue is easier, but if you'd like to break it up, you can. You could do what we did in black and just multiply your answer by 2, because it was the time it took gravity to take all of your velocity away. You could treat the second half like a drop problem if you know the distance and just find out how long gravity will allow that thing to fall for. Or how long it will take gravity to have something fall that distance. You could do red and black together if you don't trust the multiplying it by 2. But I think the blue is a lot easier. I think it's a lot quicker. That being said, let's move on to example problem number 9. This is the last one. If the juggler missed the ball and it was allowed to continue falling for an extra an extra meter, what would be the total time in air? So here's one of the things that you could do. Again, there's multiple ways you could do this. So, I don't know, style 1 or version 1. Make the problem 2 parts. I think logically, this one's a lot easier. What are the 2 parts? It's your trip up, which we already solved for, and your trip back down. So your trip up, you already know the amount of time it takes to reach the top of its trajectory was 2.2 seconds. That was the exact same thing that we solved for up here in black already, going from 22 meters per second to 0 meters per second, with gravity being the thing that caused that acceleration, took 2.2 seconds. The trip back down, we don't know, because it went up into the air, hit 0, turned around and came back and traveled an additional meter below where it was. So here's the trick. When you break it up into two parts, you could ignore the entire beginning of this and just treat it like a drop problem. What do you know about its trip back down? Well, if you start at the top, its initial velocity is going to be 0 meters per second, because the velocity at the top is always 0 meters per second. We won't know what its final velocity is. That's not important. We need to find time. We know gravity is the thing causing it to accelerate, and your change in position is now a negative 25.2 meters. It went up 24.2 meters, and if it falls an extra meter below where it was, there's your change in position. And so we can use that same equation that we used in the last problem, 1/2 AT squared. Negative 25.2 is equal to negative 5t squared. I just simplified the 1/2 of acceleration, and you're going to get, I believe it's pretty much the same number, divided by 5, 5.04. That's equal to t squared. We're not done yet. Take the square root. And you're going to get 2.25. Add those two together, and that's your total time of flight. I think that's a lot easier. The other way that you could do this, if you prefer doing this in one step, I'm going to make this green. You could treat the entire thing as one long problem, because it will go up, it will reach 0, turn around and come all the way back down. You can treat that position, your initial position, as 0, and you can treat this final position as negative 1. 1 meter below where you started. And if you do it that way, then you're going to have a initial velocity as it left your hands, 22 meters per second. You don't know what the new velocity down here will be. You can't use that one, just like you couldn't use it on the trip down previously. You're looking for the total time of flight still. You know gravity is still doing the accelerating, and you have a change in position now of negative 1 meter. So, same equation, but you've got to use the long version, right? Because your initial velocity is not 0. So it's going to be negative 1. Let me write it out for you. Your change in y is equal to v sub 0 t plus 1/2 at squared. Plug in everything that you know. You've got 22t plus 1/2 of negative 10t squared. Here's the catch. Here's why I don't encourage people to do this. It all depends on how good you are with mathematics. You have a term that contains t, and then you have a term that contains t squared. Those are not like terms. You cannot add them. If you're solving for that variable, you've got to rearrange it, the whole thing, so that it fits the quadratic formula. Rearrange the whole thing so it's set equal to 0. Basically, you could add the 1 to both sides, keep the negatives in the correct spot, and then you can plug it into the quadratic formula and solve for t. It works. That's why I put the quadratic formula on your cover page. And you'll get the exact same value. It'll work out to be, 4.45 seconds. You'll get 2 solutions out of it. I believe one of them is negative, which doesn't make sense because you can't have negative time. But you're going to get the same 4.45 seconds you would have over here after you added those together. So that is why I prefer to break it up into 2 parts. When I teach this in regulars, we break it up into 2 parts, but this is honors. You guys are a little bit better with math. If you want to do it in one quick step, it's a lot faster just to use the quadratic, but if you're uncomfortable using the quadratic, you can do it the long way, and you'll still achieve the same results. That's one of the things I love about physics is it doesn't matter how you go about doing it, so long as you show your work, you put your numbers in the correct places where they belong, and you follow the basic rules of algebra. You can get there as well. So that was it for the example problems that we had done together in class. If you do have any questions at all, don't hesitate to ask. This follows assignment 4. We'll have problems like this in the quiz. We'll have problems like this in the review. Plenty of time to practice and go over them and make sure that we're okay with them, but I don't know that you're struggling if you don't ask me about it. So message me on Teams or stop in before school sometime. Just make sure I know that you're coming so that I can be here. That's about it. Let me know if you guys need anything else.